Hi everyone. So our project is HiP-CT vasculature segmentation, which is AI-driven precision for cellular senescence analysis. Our team number is 135, and the team members are Sami, Mushtaq, and Sungmin. So the motivation of our project is that our project aims to enhance the Vasculature Common Coordinate Framework, which is VCCF, by using data science to automate the segmentation of vasculature from high resolution images. Currently, it is reliant on laborious manual annotations, and our work could transform the understanding of how cells and vasculature interact and improving the blood flow models and cellular locations across different ages, sexes, and body conditions. The problem statement is that we aim to achieve this project. What we aim to achieve through this project is to develop a model to segment blood vessels using 3D hierarchical phase contrast tomography, which is the HiP-CT data from human kidneys, aiming to enhance the representation of vasculature in the human body. So our data set comes from two different sources, and it comprises of high resolution 3D images of several kidneys along with 3D segmentation masks of each of the kidneys vasculature. The kidney images were obtained using HIP-CT, which is hierarchical phase contrast tomography CT imaging. So HIP-CT is basically an imaging technique that obtains high resolution 3D data from ex vivo organs. So our data set consists of five different classes, which are differentiated on the basis of resolution and on the basis of which kidney is being shown in the image. So, for instance, kidney 1 dense, which is one of the classes, focuses on whole of the right kidney and has a resolution of 50 nanometers. And there's another class, kidney 1 void. Similarly, there's kidney 2, kidney 3 dense, and kidney 3 sparse. So one thing that we noticed in our data set is that the pictures of our kidneys have different sizes. So in order to train the model, we had to go and pre-process these images and make sure that all these images are of the same dimensions for the model to train. Also, the data sets are of different sizes, and the size of the segmentation mask is really small. So now we move to a baseline model. We have used a ResNet model because the ResNet architecture is designed for binary image segmentation, which combines the different convolution layers, batch normalization, and the residual blocks for enhanced feature extraction. In our training, we have used 20 epochs with a batch size of 4 for each of the epoch, and we have integrated class weights in order to address the data imbalance and early stopping to fine tune the validation dice coefficient. The ResNet model's architecture is as follows. It has VGG19, which uses deep convolution layers, but it suffers from high computational complexity and a risk of overfitting. So the plain network simplifies the VGG design and reduces the number of filters and or in turn the computational complexity in order to provide a more economical and an efficient model. Then there's the residual network, which is the ResNet, which adds shortcut connections to solve the training problems of deep networks, maintaining computational efficiency while enabling deep learning. So the metrics that we used in order to check the performance of our baseline model were precision, recall, F1 score, confusion matrix, and dice coefficient. This is the result that we received from our baseline model. The first column is the input images, the second one is the predicted images, and the third one is the ground truth. The result of a baseline model were that it received an accuracy of 92.47%, which is really good starting point for a baseline model. It also has a precision of 80.52%, which means that out of every 10 positive predictions, 8 were truly positive. The F1 score is a 0.86, which strikes a good balance between the precision and the recall. Now we move on towards the improvised model. We had to overcome these two limitations of the ResNet model. One was that our baseline model lacks the capability to provide pixel level precision and detailed localization necessary for this image segmentation task. Also, the ResNet model does not effectively utilize multi-scale features, limiting its ability to recognize complex image patterns across varying resolutions. And hence we attempted to use the ResUnit model in order to increase the performance and in order to make the model better than the baseline model. So this is the architecture of the ResUnit model. The left downward branch is called as the encoder, the right upward branch is called as a decoder, and we have a ResUnit block and also a pooling layer. So the results of the ResUnit model were really great. We received an overall accuracy of 99.93% and a precision of 92.93%. And these are the different formulas that we have used in order to calculate the other metrics of the ResUnit model. As you can see in the graph here, we have represented the different classification metrics for the ResUnit model. Also, this graph shows how the training and the validation loss decreases with the increase in the number of epochs, and the training and validation dice coefficient increases with an increase in number of epochs. This represents the confusion matrix, which shows the number of true positives, true negatives, false positives, and false negatives. This is the comparison of our baseline and the final model, and we can see that all the four metrics, that is accuracy, precision, recall, and F1 score, have significantly increased in the final model, that is ResUnit, when compared to the baseline model, that is ResNet. So the conclusion that we have come across is that the unit architecture in the res unit allows for capturing multi-scale features through its expansive path, which helps it attain better accuracy when compared to the ResNet model. And the res unit is specifically designed for image segmentation tasks, which allow it to leverage its architecture for this particular type of task. And these are the references that we have referred to while making, like while creating this project. Thank you, everyone. This is our project.